There are a few more terms that you need to be familiar with when it comes to describing the subsurface and how water occurs in the subsurface. The first of these terms is known as the grain density. And the grain density refers specifically to the mineral or solid portion of the subsurface. Recall that density is the mass per volume. It's most commonly denoted with the Greek letter rho. This is a general term for density. And then we're going to put the subscript G onto it. And we'll define this as the mass of solids divided by the volume of solids. In contrast to the grain density, we can also talk about the bulk density. Which is usually described as rho sub B for bulk. And here, we're going to take the mass of the solids, but instead of dividing it just by the volume of the solids in a sample, we're going to divide it by the entire sample volume. So V total. We should note that the grain density will always be greater than or equal to the bulk density, and that the two will specifically be equal to each other when there is no pore space, namely when the porosity is 0. That is, all of the space within a sample is occupied by the solid mineral grains themselves. Now, there's one final term. It's not as common, but it's known as rho sub T, and this is the wet bulk density. So whereas the bulk density specifically refers to a dry sample, you're just taking the mass of the solids divided by the total. Here, we're going to be looking at the total mass. So including the solids and the water, and of course the air, but it basically doesn't weigh anything, so we're not going to include it. And divide this by the total volume. So these are different ways of describing density in the subsurface. There's two final terms which I want you to be familiar with, and these refer to how water, when you pour it on a sample of the subsurface, behaves and how it's retained within that sample. The first concept is known as field capacity. And the idea here is that you've poured water on a sample, you've gotten it very wet, and you're letting it drain freely. And field capacity describes the water content when the drainage basically stops, and it's the amount of water that's held in tension against gravity. And you can think about it in analogy. If you were to take a sponge, dunk it in water, and lift it up, it would drip, drip, drip. At a certain point, it's going to stop dripping, but there's still a lot of water in that sponge. The water content in that sponge is the field capacity at that time. So we will describe this as theta water content subscript FC, and it is the water content at which drainage due to gravity becomes negligible. In parallel with field capacity, we will define a term known as wilting point. Theta sub WP. And the idea here is that once this sponge is out of water, there's still water in it, but plants can still, with their roots, suck water out of that sponge, and they can pull the water up and transpire that water. The point at which the sponge is so dry that the plants themselves can no longer pull water out of it is known as the wilting point. So we will define this as the water content at which plants can no longer take up water. In other words, the transpiration has ceased. And it's worth noting that this definition really depends somewhat on the type of plant. We know that some plants are able to pull water a lot more than others. So I'm going to just note that this is plant dependent. For example, a cactus should be able to pull more water than a soybean plant. A commonly used term is the plant available water capacity of a soil. And this term describes the water content between field capacity, so it rains, it stops draining downwards, and then however long it takes for the plants to no longer be able to use that water, how much water, the difference between those two water contents. And so we will define this as the field capacity water content minus the wilting point water content.